1 septillion? 10 to the power of 24? This is the number of fusion reactors in the universe, and our Milky Way galaxy is home to as many as 300 billion of these. In our solar system, we only have one working fusion reactor, the Sun. However, this might be about to change. So, how does it work? What exactly is a fusion reaction?
If you heat up a mixture of deuterium and tritium to a high enough temperature, the electrons are eventually ionized, forming a plasma of uncoupled electrons and nuclei. But as the charged nuclei approach each other, they are repelled by a strong Coulombic force. Not much good as a power source. But heat them up even further, to 150 million degrees Celsius to be precise, and they can overcome this barrier. The nuclei then slam together, resulting in a highly exothermic reaction that produces a helium nucleus and a neutron. Mass is not conserved, and in accordance with Einstein's now immortalized E equals mc squared, this releases a huge amount of energy. In fact, a kilo of fusion fuel releases as much heat energy as 4 kilos of uranium, and 6 Olympic-sized swimming pools of coal. But how on earth do we do this on Earth?
The tokamak uses a complex arrangement of strong magnetic fields to confine a hot plasma into a torus or donut shape. The plasma is then heated to the required temperature using a combination of electromagnetic radiation and high-energy ion beams. It is at this point that fusion reactions begin.
The fusion reactor materials need to be carefully considered. The materials need to be able to withstand the high neutron flux in the reactor. They also need to not become significantly radioactive, so that they produce unacceptable amounts of nuclear waste. Finally, the materials also need to be able to cope with intense and fluctuating magnetic fields.
There are 3 main benefits to using nuclear fusion, the first of which is a virtually infinite supply of fuel. Did you know that the amount of deuterium in 1 cubic kilometre of seawater could supply the same amount of energy as the world's current oil reserves? Nuclear fusion does not produce any carbon dioxide or other harmful gases such as sulfur or nitrogen oxides, which helps to reduce global warming and preserve our precious environment. Compared to nuclear fission, fusion is a much safer technology. If the plasma is at all disturbed, the reaction simply stops, rather than spiralling out of control.
The most promising project so far has been the Joint European Torus, or JET project, at the CCFE in Oxfordshire. JET set the world record in 1997 for fusion power generated from deuterium-tritium at a whopping 16 megawatts, enough to power a Eurostar, and currently engages over 350 scientists from all over Europe. However, JET still consumes more energy than it produces, and the energetic nuclei escape from the tokamak plasma too quickly. So, what's the solution?
Bring on the International Thermonuclear Experimental Reactor, or ITER. ITER was initiated in Cadarache, France in 2006 and aims to scale up JET's progress to the commercial level. ITER employs a much larger tokamak and aims to produce 500 megawatts of continuous fusion power with only a fractional energy input.
ITER will help to confirm the viability of fusion technology on a large scale and is being run in conjunction with 2 other projects, IF-MIF, which will test the materials for ITER, and DEMO, which hopes to pilot integration of electricity into the grid within the next 30 years.
The original cost of ITER was expected to be $5 billion, but has since more than quadrupled to $20 billion due to rising material costs and changes to the design. The EU is contributing around 45% of the cost, and the first plasma is expected to be created by 2020.
Believe it or not, development in fusion technology is progressing 10 times faster than consumer electronics. So, could fusion be the energy of our future?